That's good. Welcome back. Thank you for being here. Today I promised you that we would look at applications which are in some sense a lot more accessible. So the hard work we've done over the last 2 days, I think Monday was softer, will pay off. We will start with the application that kind of motivated approximate message passing in some sense, which is compressed sensing. And then I'll give an example of a communication system that uses it as well. So just to start from a familiar point, we're looking at linear inverse problems for now, and especially in the context of compressed sensing, where, but just broadly linear inverse problem, y is equal to a wide matrix A times a vector S0. And it's embedded in noise. And so A is seen as a linear transformation, and on the right we have these fundamental subspaces that we've now become intimately familiar with that are inherited from this linear transformation. And our goal is to start from observation y and kind of get some estimate of S0. And we will do that with our composite iterative scheme, and we'll try to get to a point where we can leverage some signal structure that we have on the left in the domain of the linear transformation A. So I want to start from a general concept, and then we'll start with the easiest regularized problem, and then we'll go to the one that's the L1 regularized problem. So in general, this is the problem we just discussed. I want to minimize the norm between S and S0. And I want to do that by incorporating both the knowledge of my model, but some knowledge about S0. And so I'm going to use regularization for that. So what do I mean? So my objective is for my state, or my estimate of the state S, when multiplied on the left by A, to be as close as possible to Y in terms of explaining my observation. So it should be able to explain the observation. And then in this minimization problem, so the minimization is over both the left term and the right term, we'll have a penalty term that is going to try to capture the information that I have about the structure of S. So the easiest way to do that is to have a penalty that's a square penalty. So for instance, what's a situation where, as a toy problem you can think of, it would be something like, I want a solution to this linear inverse problem, but I also know that the energy of the signal cannot be too big. So I want to penalize the energy that I give to my solution. So in terms of this minimization, here is what I want to achieve in terms of being able to explain my observation y. So I want to pick a state that's as close to y as possible when multiplied on the left by A. And this regularizes my energy of the system, of my solution S. So I'm not letting it be too large. The over 2 is a convenience factor. So we'll solve this problem two-way, but I want to point out that the norm, the 2 norm, is the one who has circular, spherical distance. So if you take a constant norm, a level set, it's going to have this circular shape, and it gives us a quadratic objective function. So the first way I want to solve this problem I believe, is a way we're familiar with. So I take my objective function f0, and I'm going to take the gradient of it. So now, if I take the gradient of this function, something that we are familiar with, this norm is the norm induced by the standard inner product. So in some sense, it is equal to as minus y transpose times as minus y. This one is, similarly, is going to be lambda s transpose s. And so when you take the gradient of that, you get these very well-behaved expression that you can organize in this fashion over here. In terms of the variables that we had for our composite iterative schemes, y minus as is the residual, and then you have this other component here. So if you would like to do a gradient descent algorithm to get inspired about your equation, so what would you do? So you will look at your next step in a gradient descent type of way will be your current point where you are as a state, and then you're going to take a step in the direction of the gradient that gets you to the minimization of this objective. So in this case, we're going minus alpha times the gradient. Alpha here has to do with the step size you want for your gradient descent algorithm. So this is the gradient that we had on the previous slide. So the gradient of my quadratic function is going to be a transpose times z, or y minus as the residual, and you also have this contribution over here. Okay, so again, this gradient comes from this over here. And then you can rearrange this equation into this term comes from the top one. So you have this term over here, and then you combine the first and last term into this second summand. So if you start from 0, then you get these two steps as a composite iterative algorithm. So of course, we're trying to get a problem that's easy for us, a quadratic problem, and then put it in the form that we're familiar with of the composite iterative algorithm. So we'll take z as your residual, the part that's unexplained yet, by y, the observation, minus a times where you believe the state is. And then if you take the second step, then your improved state will be equal to alpha a transpose z, where I'm using now this notation as z, plus some knowledge about my state where I was before. Okay, and then we know that, so we can recognize these as being very close to what we studied yesterday as an iterative step. So we know that, well, it's slightly different because of this factor, but if we iterate through this starting from 0, state 0, then this will converge to this lambda I plus A transpose A inverse times A transpose Y. Okay, so now we have a gradient version, a gradient descent version that led to our composite iterative algorithm in a form that's very close to what we had yesterday. And then in the same manner, we can get it to know that it converges to the point we wanted. So what happens here is that because we regularize our problem with lambda s, in the solution it manifests itself by this lambda I plus A transpose A. If that lambda was not there, we would recover exactly what we had yesterday. So that's familiar territory. Over here. Any questions so far, or that's good? Yeah, so we're trying to bridge that. So what I'm trying to do is take a problem that we are very familiar with. I think anyone who came here could solve a quadratic problem in their sleep before they came here. But I want to put it in the, trying to motivate again what we're talked about for the AMP algorithm, where you have a residual, then you have, you go to the transpose domain. This part corresponds to what we were trying to do when we did some denoising. So how are you going to denoise? Well, if you're penalizing, in some sense, the energy of your signal, this is acting as if the prior knowledge comes in the sense of saying my signal cannot be too large, and this reduces the magnitude of the state in the previous step in some sense. So it's trying to draw an analogy between what we say by using side information in the second step of the composite algorithm. But it's no more than that. The value of lambda, that, so for this problem, it's just abstract. The value of lambda should be guided by how you think the energy of the signal is. But I don't have a straight answer for you. In fact, we'll look at the second problem, the L1 regularized problem, and there, that question was researched for quite a while. In fact, you can get a shrinking lambda, and recently, a few years ago, Donahoe had some principled fashion to pick the lambda for certain problems. But it's not a straightforward answer. So I want to look at the same problem, but I will look at it in a slightly different way. I will look at it in the context of proximal gradient descent. And specifically, we're looking at proximal gradient descent, not to solve this problem. We already have the answer. We did it on the previous slide. We're doing it to get familiar with the notion of proximal gradient descent, because we will need to use it for the L1 regularized problem. And this really becomes a very handy tool when your objective function is not differentiable everywhere. So here you can think of this. I'm going to reformulate. This is my objective function. And what I'm going to do is I'm going to linearize in the Taylor form that function around my current state st. So this is a global view of my function. And I want to do a Taylor series expansion of it around st, where I am right now. So here, f0s will be equal to the value of the function at st plus the gradient transpose applied to the difference between s and st plus some higher order terms. And I'm going to argue that for a small step, this is approximately equal to the 0 order and the first order term. So this is similar to a Taylor series expansion, keeping only the 0 term and the linear term. And I am going to take this function and put it in a proximal objective function. So I'm trying to look at it around where the function was linearized, and then here I'm going to control the step size with this second function over here. So what do I mean by that? So if alpha becomes small, the price of this becomes very large. So if I want to take a gradient descent step that is smaller, all I have to do is take a smaller lambda, and we'll see how it comes out. But you're just trying to do a localized, so proximity, a localized search for what you want, and you're looking at the linearized version of your function with this this function being accurate locally, and then you're forcing it to look only in a neighborhood with this quadratic. Okay? So I can make this step size arbitrarily small by going with a very small lambda. So for now, we're still in a domain where everything is very well behaved. So I can solve this particular proximal gradient descent by taking the gradient of the objective and then applying the KKT condition. So what do I mean by that? So if you take the gradient of the objective, you're taking the gradient with respect to S. This component here is going to give you only the gradient of F0 st. And maybe this is what I mean. So I am interested in taking the argmin over S. I'm going to take the gradient with respect to S. The first component is a constant. There's no S in it, so it's going to vanish. This is the S minus st vector folded over the gradient. So I can, with the linearity of the inner product, I can break it in two. And then when I take the gradient with respect to S, I will only have this term remaining. And then here, this can be viewed as S minus st, inner product with S minus st. And again, I can take the gradient for that, and I will get the factor of 2 because it's a quadratic. We'll cancel out with the factor of 2. That's why it was introduced in the first place for convenience. And I'm left with 1 over alpha S minus st. Now I want to, for optimality, I want this to be equal to 0, and then that brings us to the last line on this slide. Yes? This over here? Yes. So if you look at it, we're doing something slightly different than what we did last time. So we created this function, this truncated function, and now we're put it in here, and so this is a proximal. So if I'm looking at only things in proximity, I can take kind of the expansion, kill the higher order terms, and then regularize it over here. I beg you. Yeah, so this is, oh, you're saying I'm missing the lambda, or? So that's, I'm not sure what so first of all, you're saying the mean square error, but this is not random right now. And then, did I drop the lambda? Yeah, it seems I dropped the lambda. But this will force, it's a regularizer in the sense that it will force a smaller step size. Is that what you're asking, or no? Okay. So it forces the step to be smaller than it would if you were not there. So you've linearized this, right? So this is now kind of a linear objective. it's locally accurate, but it's not globally accurate. In fact, you cannot have an unconstrained linear objective. You will just go down the linear line. So you're controlling your step size on the linearized problem with that regularizer term. Yes?
Okay, what would be the connection from alpha to lambda now? Do they get constrained?
Yeah, so I think I just, yeah, I am not sure why I switched the lambda per se. I think this technique here is,
No, that lambda stays because that's in part of F0. So
yeah.
Say
Yeah, so this is all sorry, yeah, this is all in here. You're correct.
so lambda and there are two parameters now.
Yeah, so I wanted to show the technique with a function we're familiar with. Of course, for this particular problem, because we know the solution, it's not needed to use this scheme, but I will use it for the other one. And thank you for pointing out that the lambda is embedded in there, so my objective function is completely linearized. And then this will regularize my step. Now, there is one subtlety. So lambda s squared is a quadratic term, but once I do this and I disregard the higher order terms, I have taken the linear version of it locally.
Can we replace 1 by alpha by lambda?
No.
Is alpha a different parameter or it's alpha the gradient descent parameter?
So lambda is not the gradient descent parameter. This will, alpha is the gradient step. So what I'm trying to say is, if I want to take a gradient descent approach to a function, generally speaking, one way to do it is to linearize that function, the entire function, by taking the first two terms of the expansion around where I am. That's this part. So if you had a quadratic function in some sense, now you're using a local plane that's tangent to that function. So you've lost the quadratic part of it. But locally, that plane being tangential is very accurate. But it's only accurate locally. So since I've linearized the plane, I need to control the step size still. Because that plane, while it's easy to go along, is not accurate if I go too far. And in fact, if I were to try to minimize a plane, it would just go the wrong way. So I need this factor to control the step on that linearized problem. It's a little bit contrived here because we have a quadratic problem, so that we can solve firsthand.
But the lambda still controls the angle of the plane,
So the lambda will be there. It will contribute to the normal to that plane, or at the angle of the plane. Yes, that's accurate.
Sir, there is, when you cancel phi 1, f naught of this thing, the first one.
So I'm taking the gradient with respect to s. So this is a constant as viewed from the derivative. Okay, so just the gradient descent step for algorithm now is going to be equal to s is equal to my current state minus alpha f0 st. Okay, so again, we have this over here. What do I do to get the gradient step? I can take this term and put it on the other side, and then I multiply by alpha. And I get that st should become alpha times this over here. Okay, so I'm making a gradient algorithm based on this. It's a gradient descent that's inherited from my proximal problem, optimization problem. In this step, what I do is I replace the gradient of f0 evaluated at st by the value that I had computed previously. So it's a substitution. Then I can rearrange the terms over here. So I rearrange the terms so that it starts looking like what I wanted, a residual z and a linear term. So it looks essentially the same for that particular algorithm, except for the size of the alpha that controls my step size. Okay, so we have two ways of solving the same problem. This is just to get some confidence with proximal formulations. So now this is the problem that we are interested in, is the lasso or L1 regularized problem. So that problem has a long history that date back decades, but around the 2000s it was identified as rigorously as a proxy for an L0 norm, giving you regularization with the L1 norm, giving you a very good proxy for the L0 norm, and under certain conditions being able to solve for sparse problems. Before I do this, I want to get to the board a little bit to talk about the L1 regularized problem. So if you think of the absolute value function, so if you think of L1 in one dimension as the absolute value function, so this function looks probably very familiar to you. It looks somewhat like this. And the only thing that I'm going to put on this side of the board is I want to emphasize the fact that this is a function that is not differentiable at 0. So the derivative over here is quite obvious, but we have to deal with the fact that it has several tangent line that will touch that point. So conceptually, there's nothing much there, but there's not like there's not a derivative at this point. There's a subdifferential. And the subdifferential is a collection of lines that are all below the convex function at that point. And there are many, many such lines. And then we know from optimization and convex optimization that a point will be optimal. If it's not differentiable, it will be optimal if the 0 is in the subdifferential. Okay, so the line has to be horizontal. Maybe I should say something that would not be optimal where you have a subdifferential would be a function that looks maybe like this. So this point here does not have a differential. It does not have a derivative, but it has kind of a subdifferential, but it does not contain the 0 subdifferential, so it's not optimal. You can go down. It's easy concept. So we will use that very briefly. So I want to look at this problem here. That's a centralized version of what we'll do in a minute. So we start, again, with an easy problem, and then we'll step on to a more general problem. So here I have 1 over 2 eta u minus x squared plus u1. So I can think of this as so when we're in this context, we think of it as wanting to minimize the first component subject to a regularizer on the second component. But when we think about it in the context of the board on the right, we think of it as wanting to minimize this subject to a locality constraint. This now looks, because it's a quadratic, that's a very well behaved, and then this eta is going to control our step size. Okay, so these are two ways. We'll look at it for the optimization of one. So if I try to take the gradient of this, what is going to happen? Well, you're going to have something like this. You're taking the gradient of u minus x inner product with u minus x. So you're going to get 2u minus x times the constant. So you get 1 over eta times u minus x. Okay, that's easy. For the second part, you're a little bit in trouble in the sense that there's no gradient per se, but there's a subdifferential in most points. We'll have a gradient, but for the rest, you do not. Okay, so if I think of my optimality condition that I need 0 to be an element of this, just like I needed the zero derivative to be at the bottom, to be part of my subdifferential for the point to be the minimum over there. Okay, so now let's break this down into 3 cases. This problem down into three cases. And these 3 cases are informed by what is happening here. So for instance, we'll start with when u is greater than 0. So this is going to be well behaved there. The gradient of the one norm of u when u is greater than 0. I guess I'm thinking scalar-wise here. When u is greater than 0, this is going to become 1 over eta u minus x plus 1. Okay, so if I want this to be optimum, then this should be equal to 0. So that's going to give me an equation that u should be equal to x minus eta. So I set this equal to 0, and I solve, just like I would for a standard problem. I get u is equal to x minus eta. But I'm slightly more constrained than this. So in the sense that this will be true provided that u is greater than 0. So really, this will only work when x is greater than it. The other part is equally easy, which is the one where u is less than 0. So in this case, if I translate this equation when u is less than 0, I'm going to get a minus 1. And this is going to give me, if I set this equal to 0, put the 1 on the other side, cross multiply by eta, and isolate the x, the u, I get x. Oh, you're solving this. Yeah, okay, sorry. Yeah, x plus eta. And then this will work provided that x is less than minus eta. Then we come to the last part. I'm going to reclaim the top of this small board. So at 0, this becomes a set. What is the set that it becomes? Minus 1 to 1. So then I have that 1 over eta times u minus x plus the set minus 1 to 1 should contain 0. So that's shifting my set in some sense. So I get, for this to work out, I get that x should belong to minus eta to eta. Okay, so maybe like this. I'm going to replace this by this set. And so I'm here, but how do I get rid of the u? Why is the u going away? Yeah, this equation only works for u is equal to 0. So then I get, this goes to 0. The minus can be taken to the other side, but that set is currently symmetric, and then I put the eta on the other side. So you get this form at the top. So what you end up having is kind of this function that is linear, flat, linear. Okay, so I just wanted to show that with the easy case. Now we look at it here. It's going to be a shifted high-dimensional version of the same problem. So let's go through this. So we have an L1 regularization. So that's typically more robust to outliers, for instance. And the additive cost is the sum of the absolute values of these components. So this is our problem. And again, the minimization here runs over both summons. So we want to adapt the idea of the proximal gradient descent to this particular non-smooth L1. So what are we going to do? We're going to take our function over here and then linearize it around a point, st. We take the well-behaved part of the function, and then we'll have this over here. So you can view it. So what do I mean by it's equivalent to trying to minimize this regularized or with the step size controlled by this over here, just like we did before. Okay, and F0 in this case is going to be this over here. So if we do that, we go to the optimality condition that are going to look very similar to this, but in higher dimensions. So if your function is in general not differentiable everywhere, so you have to deal with the possibility of having subdifferential. So you're going to have optimality if 0 belongs to your subdifferential, just like we did over here. And then you can move from the top line to the second line by replacing. So this term is going to vanish. This term is going to come out. This is going to lead to one linear term with the 1 over alpha. And this comes and captures the subdifferential. Okay, so this, having 0 in this is equivalent to having the first term minus the first term belong to the subdifferential of there. And then we can rearrange this step like we have done a few times already into something that's familiar with, and a state update and a residual. So with that, we get, we have to do the same thing that's going to lead to the high dimension version of this shrinkage function. We isolate S, we get something that looks like this. And so we have a proximal gradient descent function that looks like the update, ST, should be this shrinkage function of the argument. To go from here to here is essentially the same that we've done with the easy function in one dimension. This is going to be in a higher dimension. So one way to write the shrinkage is you're going to take x sk minus, so it's applied component-wise. You're going to take the absolute of sk minus alpha lambda. So you're trying to see if you're in a scenario where one of these two things will apply, or if you're going to be in the flat scenario. That's essentially the positive part is going to do. If you are in this scenario, then the slope is going to be linear. So that's how you have that linear component there. But and then if S is small, Sk is small, just like here when x was between, absolute value of x was between minus eta and eta, this is going to become 0. Because you have a small term minus something positive, you get negative, and the plus sign will make it equal to 0. So this is essentially a way to express this function over here. So what does it look like? It looked like the shrinkage or self-thresholding function. It's given by this, and component-wise it looks like this function, is what we want to apply in terms of taking our L1 regularized problem at every step. So what do I mean by that? Now we get something called, it has several names. I guess I called it iterative shrinkage thresholding algorithm, ISTA, and sometimes it's also called iterative self-thresholding, IST. So it has a few names, and it's been researched quite extensively. What this does essentially is it's trying to take into consideration the fact that, for us, in our context, the fact that the vector is sparse. So we use the L1 regularization because we know, so we've used in our back pocket knowledge that's already established that that's a good proxy for an L0 norm when the vector is sparse. Once we decided to go with the L1 regularization, we wanted an iterative scheme. We used proximal gradient descent to find the iteration. The iterations are of this form, where at the top you compute the residual y minus AST. And at the bottom, you update your state by looking at this term that we're familiar with, A transpose ZT plus ST, which we call the effective observation. But this time, we have to do something to it, something that captures what we know about the problem. So we know that the problem is sparse. We know that L1 is a good proxy to L0 for sparsification, and we designed that function based on that knowledge. So our iterative scheme now has two steps, but the second step as this denoising function, this denoising component that captures the knowledge that we have about ST. Any questions thus far? Okay. So I wanted to, I guess, tie this more closely with the compressed sensing problem. The compressed sensing problem is high dimension for us, linear regression of this wide matrix times the tau vector in this underdetermined problem. Sometimes there's a z, sometimes there's no z, whether it's a noisy compressed sensing or not. What we're given is observation y, and we know perhaps that S is sparse. So if we know that, then the L0 norm would really be the right thing to look at because it captures the sparsity. So we would want to do something like this. Minimize the unexplained part of the observation y subject to the sparsity constraint. But we use a convex relaxation. We use the convex relaxation of the L1 norm. The L1 norm now is spiky. It's not round. And so that's why it's going to lead to a function that's not differentiable everywhere. And we use the lasso as a proxy. So there have been like quite a few algorithms. This is a very well-studied problem. It's a very well-studied problem, not only in the past, up until recently into some aspects of the problem. So once you do the lasso, once you regularize with the L1 norm, this problem is convex. It's going to be well-behaved. We have the iterative self-thresholding algorithm with or without momentum. We've seen the one without momentum, but not super long ago, Nesterov introduced a momentum term that really accelerated the convergence of this algorithm. And then there are other formulations. For instance, you could have a non-negative least squares or a non-negative least absolute deviation version. So, and this algorithm, and then recently there was a paper a few years ago by Dono telling you how to pick the lambda. And then these algorithms have been API'd out extensively. So if you want to use them as a pedagogical tool and play with them, it's very easy. So we want to look at the M version, the approximate message passing version of this particular iterative algorithm. So we will strive for low complexity, and we'll assume that we have a very high dimension problem. One of the reasons we want to assume a high dimensional problem is because the theory we've developed, some of the steps that we've done yesterday, was for large matrices. So if you take a very small matrix, it's likely to not apply that well. But if you have a very small matrix, your quest for low complexity is not as important. If you have a very large matrix or a huge matrix, then a low complexity algorithm is of paramount importance. So this is our setting. And our objective is going to be this objective over here. And what we want is we want an AMP interpretation of the algorithm we've seen on the previous page. So we'll get to design or see what the Onsager correction looks like for this particular term. So this is the iterative self-thresholding algorithm that we had just a few slides ago. So you compute the residual, you compute your effective observation, and then you denoise it with this self-thresholding function. So this has almost all that we want in terms of creating an AMP algorithm, except that it's missing the Onsager term. So luckily for us, the unstaggered term, if you think about it, for this particular function is fairly easy. So think of this function here. This function, I'm not sure what's on the first page. Okay, let me use this one. This is the same content, but without ista, but with the unstaggered term in the bottom. So you have to apply the self-thresholding function pointwise to your vector. And you have to get to the unstaggered term, you have to compute this div operator, or you have to compute something that's like this. You're going to sum of every component. So you're looking at a vector function, but it's applied, the vector function for us is separable, it's applied pointwise, and then you take the gradient, or the partial derivative with respect to the diagonal component, and then you sum them up. Well, what's going to happen to this for our self-thresholding function? It's going to depend where you're looking at it, okay, which component you're looking into the vector. But suppose we think of a particular component. For a particular RK, this can take only two values. Okay. If the RK happens to be on this slope, the value is going to be 1. If it happens to be here, 0, and here is 1. So when you're looking at this and you're summing over all the components of your vector, you're really looking at kind of the number of, it's going to be related to the number of entries that are non-zero in your vector. So here, this is where this comes from. It comes from counting the number of non-zero entries in your vector. Remember that the unstaggered term, or the correction that we had, has the vector that comes out of the application of Stein's lemma in some sense. So that's this vector over here. And then it had a constant term. The constant term for us is going to be this. The div, and you can hear the n is over here, so it depends how you define it. So, but yesterday I put the n with the computation of the div, but you get this term here that should be very familiar. And then I'm going to ask, so this is it's as simple as that. This is the approximate message passing version of the ISTA algorithm. So I want to ask you a question. We shied away from the L0 norms over the optimization because we said that's too complex. But then the 0 of the S vector comes here. So it came back. Why is it okay that it be here and it was not okay that it be there? That's exactly the answer that I was hoping for. So his answer was that optimizing over a vector of a certain L0 norm is very difficult because it's a combinatorial object. And you have just a scattering amount of possibilities. But computing the L0 norm for a vector, that's trivial. So it's okay that in this step we don't have to optimize over an L0. We just have to count the number of non-zero entries. So that's easy. So that's the full form of the AMP algorithm for this particular one. Now, I don't have a graph for you that compares the performance of the two. And I do not have a graph for you because I believe Lakshmikant sent an IPython notebook to you so that you can upload it to a Google Drive if you have one, and then just run it as a Google Colab. And then if you just run the script or run the notebook, it will give you one instance, and it will give you the curve for one problem, it will give you the curve for the other problem, and then it will give you the comparison between the two. But it will also give you a shell of a code that you can play with. So if you want to look at different sparsity level, different matrix sizes, or if you want to look at a different regularized problem. So the answer is on how well it does is on the practical session today through your IPython notebook. Any questions? Yes. Yeah, so the momentum would be typically based on the gradient. Here we can only do it in one direction because of the z is fixed, right? So you're not based on how you took that step per se. But I think there are some flavors of that. So I cannot give you a more complete answer to that. There seem to be some flavor, but it's not equivalent. I do not think it's... Yeah. Yeah, I think that's a good observation. Okay, we're at the break point, aren't we? We take a break, 15 minutes. Thank you.
What's the difference between the proximal operator and proximal gradient descent? Like whenever you started writing proximal gradient descent, like this formula, this actually looks like it's a proximal operator where you have the same minimization of a function where with respect
Yeah,
to
so we're using a proximal up, so the
proximal operator for this L1 norm is exactly the soft threshold
yeah.
operator. So
Yeah, so that's where it's from. Yeah, so like we would have like a prox like this. So we have like our objective function plus the square, right? So we'd have like maybe some objective function that's linearized and plus some quadratic term. Yeah, depends where you are, but yeah. So
this is your prox operator.
So that you get this by using your acting on your prox optimization. You're doing exactly what you're thinking. So instead of trying to get the gradient from the top there, you're doing the prox operator over the linearized model, and then you get the shift. Yes, so that's where it's from. If you're familiar with, I did this for the people who have not seen it before. But if you've done optimization, it seems before. So then.
Like my work is related to compress sensing. So,
Oh,
like I've gone through.
Okay, so maybe he gave the talk this afternoon then.
No, currently I'm using this proximal operator rather than for L1 norm. I'm looking at more. I'm trying to induce different structure sparsity, like piecewise sparsity, group sparsity, these kind of things where you have mixed norms coming into the picture, and they use this proximal operator extensively because
Yes.
you don't have, most of the time you have L1 norms or L2 1 norm kind of things, we have mixed norms, so then you don't have a gradient step. They write it proximal, you use the proximal operator to compute the gradient and do
Yeah, so that's, you're correct. So you're using the proximal operator because you're not guaranteed to have a gradient.
Yes.
So if you want to have a gradient descent, you use the proximal operator gives you a proximal gradient.
And one other small thing.
So like in general, like you have gradient descent, and if you have some conditions on your convex function, you can get some guarantees, and then you can have like something like a subgradient descent that's known to be slow typically.
Yes.
And you get to the proximal formulation, then you can get an algorithm for non-differentiable functions that can be quite good in terms of performance. That's exactly, we're doing that here to define how we're going to create the iterative algorithm.
In the talk you referred to, there is one paper where, don't know who, gives
the
where
lambda
lambda, how
and
to pick lambda.
Yeah.
Is it last algorithm that you're referring to, or the homotopy method where
Yeah.
you actually
Yeah.
find lambda in a sequential manner,
Yes.
so that you start with the lambda? So that's the paper that you.
Yeah, I think so.
Okay. Because in one of this computer sensing textbook, which is released in 2013, like that method is given. So when you said recent, like
No,
how
not
recent?
not that recent.
Okay.
Yeah, I mean recent in terms of, I mean that lasso problem is, I don't know.
Yeah, it's very
been
old.
there for eternity. So it's
Like-
kind of funny that.
The last papers that I think about this computer sensing date back to 1991 time, and there is a resurgence in 2005 because of the Candace and Terence Tao, where they use
Yeah.
this linear programming for finding.
But like, but L1 was there
Yeah.
like before that.
Okay.
So like in the 70s, they used L1 for certain, like, I think geophysicists used L1 for translation for some of their problems.
Yeah.
Yeah, good. Your intuition is correct. Yes.
I have like basic doubt that here the sparse is S. S is sparse. S is a vector
Yes.
which is sparse, and we are
Yes.
trying to approximate
Yes.
it as close to Y as possible. So the A is
So
A is
we don't
known.
want S to be close to Y. We want
A is to be
yes,
close
yes,
to B. Yeah.
yes.
A is known.
A is no.
Okay. Actually, I'm trying to do a similar problem, but not this, in where I have distributed sensing nodes in a home environment or wherever, and they're continuously sending sensing data like the channel state information or any other vector to the server. I'm trying to minimize the size of the data which is being sent, while also trying to approximate the data it actually was. So in that case, but the size, if original S was of size 64 and I'm trying to send only say 10 or 20, and then I'm still trying to achieve the goals which 64 would have achieved. So in that case, A won't be known because A is the channel.
Yeah, so your channel has to be estimated. I'm not sure.
Yeah. So the channel will be estimated at the receiver already.
Yeah. So.
But then it will receive an S, which is of lesser size than actual Y.
Right. When the channel is not known, there are techniques that we will not get into, but for communication, there are techniques. It's not quite your problem. I don't know how dimension reduction is going to affect this, but there are techniques where you're trying to both get the signal and estimate the channel, and you do it through bi-amps. You do one amp on one side trying to estimate the signal. Once you get better with the signal estimate, they go and they amp estimate the channel, and then they go back and forth.
Okay. So in this case, Y and S are of the same size, but S has very many less entries than Y.
Right.
So if Y was a non-zero vector, S is a sparse vector, but it is trying to emulate Y or something.
Yeah. So it's not. So I. It's
So
not
what
taking-
I'm trying to say
Yeah,
is,
no, I know what you mean.
Y is equal to
you
Hx
don't
plus
have
N.
an underdetermined problem.
Yeah, Y is equal to Hx plus N, but instead of like X is the original vector which was being sent, H is the channel, N is the noise. I'm trying to send very less amount of X rather than the big one.
this problem is also came up in for machine learning and
Yeah.
in
So
this classification of the gradient.
I'm trying to do sensing using channel state information wherein
You can use it for that.
yeah, but then A is unknown.
Mm.
A is
But
unknown.
you estimate it, right? You can
Yeah, we
estimate A and
estimate
then iterate it to
But then
A.
Y is also unknown to the receiver, no?
Correct. But something
So
you have to estimate. No,
most
you
of the
can't have both
things
the
are
things
unknown.
right? One should be estimated and find out the other.
Yes.
Then
So you
solve
can
the
go-
problem. Yeah.
You can go back.
Iterative algorithms type of thing. Joint iterative.
Yeah, I will.
Yeah.
Thank you. Thank you.
This on-stage you have shown.
Yes.
Yeah, what does it mean? What is the literal meaning of on-stage? That's a
So
person?
That's a person.
Oh, okay.
So that the theory comes partly from statistical physics.
Oh. He's a Nobel laureate in chemistry, it seems, is it?
I don't know.
Okay. Yesterday, suddenly I
But,
got a message like he's a Nobel laureate in chemistry.
That's but like this is what happened.
Okay.
Physicists, I don't know how they do it.
You were talking to that guy, no, from physics
Yeah.
department, yeah.
But they get the solution of the problem before they solve the problem.
Correct.
So my understanding is not for these equations, but for a physics problem, maybe the tap equations, which I don't know much about, so I'm not going to venture on that ice. But he realized that if you added a correction,
Okay.
the estimates of the state, the predictability of their equations for the states of the physics would work way better. Now
That is similar to that prediction error what we transmit in video coding or DPCM type of a thing.
yeah, but to come up with this is out of the if you
Oh,
don't
we
do
were not
this-
doing in the optimization step.
Right.
Now we are doing it in the optimization
Right.
step. So reduce that error also and then find the
But think about
unknowns
the
also.
form of this.
Oh.
So we got the form of this like I think the conditional proof that we went over yesterday, that's a phenomenon.
Oh.
So they got a structured way to explain something, but one person got this without really knowing where it's
That
from.
we will use it here and
Yeah,
all.
we'll use it here and things work so much better.
It is similar like the entropy equation what we use for coding nowadays, no? That it came from mechanical type of a thing, that mechanics and all those. Entropy.
Yes.
So heat and all those.
Yes.
Yeah, similar.
So similar, but like the physicists, they see the solution like before they prove the solution. I always find that
Correct.
they're very creative. But I think also that
They don't think of the applications part of it. They just to try to find a solution for the given problem.
they want the solution. They like even if you think of like Gerard when he started, like he was not worried about having a super rigorous mathematical foundation for things he knew would work. So they get there, and then after
Correct.
that, like mathematicians, like
Take it up and
They
then
make it work,
finally
make it rigorous.
electrical engineers also
Yeah.
did. Want to
Yes.
have coffee?
no, I'm gonna just stretch out a little bit.
Okay.
Not talk.
They say he's a Nobel laureate in chemistry.
Yeah, that's possible. Yeah, I don't know the.
Hello. Mic test, mic test.
Welcome back. We're doing something new. So I want to show a different application of AMP. And that application specifically, you can ask any question, because that's for the first time I get to present a little bit of my own work. So I'm pretty excited about this. We'll see where it comes from. So the outline for the afternoon is we're going to review sparse regression code. So sparse regression code were introduced by Andrew Barron and a collaborator a little while ago, and this is really the first application. So it has a sparsity structure, and it has some nice property, like it was shown to be capacity achieving. And then subsequently, with some of his students and also in parallel with some other group, we'll see that, they applied kind of sparse recovery to it to show that you can get to capacity with low complexity scheme. We did a twist on this. We looked at sparse regression and then married them with LDPC code. So that's really what we are going to look at as an object this afternoon, this second part of the morning, from an approximate message passing point of view, and trying to also leverage belief propagation, the standard graph belief propagation for graphical model. And then we'll offer some potential evidence on the performance of these schemes. Okay, so let's see what this looks like. To begin, I would like to talk about one way to look at a code book. So in wireless communications, to protect messages from errors, we use error-correcting codes. So these codes typically have a level of redundancy that shields the information you're trying to transmit from the noise or the fluctuations of the channel. The way it works is that if you have so for block code, if you have a message with a certain number of information bits, then you encode it, and that gives you a vector of symbols that you transmit over the wireless channel. Since wireless was part of the summer school title, or communication was part of the summer school title, I will assume that many of you are familiar with that. So I want to think about coding a slightly different way. I want to think about it in terms of you're going to map every possible information message. You're going to think of it as what happens when you encode it. You get a sequence of symbols that we're going to think about as a vector. And then we're going to stack them in the form of a matrix, just as a mental exercise to get the conversation starting. For instance, here this F that I have on the board there is my encoder. And what's inside the F is my information bits. In this case is 5 zeros. I put it in, I get a sequence of symbol, and I stack it as the first column of a matrix. I looked at my second possible message, which will be the all zero message except for the last one, which will have a 1. I encode it. The encoder gives me a sequence of symbols that I would normally want to transmit, but I'll stack it as a column of this matrix. And I continue doing that. Now, if you look, the argument of my function is binary because typically information is seen as binary. But irrespective of that, I go from all the possibilities that I have into stacking a matrix. And I end up with a matrix that looks like this. Since these are the sequences of symbols that I want to transmit, if I want to, I can think of it as time going from top to bottom, and you pick a column, and then you transmit one symbol from top to bottom. And that is an abstract way to think about any block codes, generally speaking. So if you think of your function, it takes b bit as its input. And the signal is of the output of your encoder. Now, another way to think about it then is to say, I'm going to select this message, the message I want to send, the encoded message, by using an index vector. So what do I mean by that? I'm going to look at the binary version of my message, for instance. I'm going to interpret it as an integer. And I'm going to put a 1 in the location that I found that integer, and 0 everywhere else. So then, if I take this vector and fold it over my matrix, I recover the encoded version of this message. Okay, so the matrix is quite wide. If I'm sending 2 bits, the width of the matrix is 2 to the b. 1 for every possible message. This vector has the same length, and this is some sort of index. We call it the index message because it has zeros everywhere and 1 at a specific point. In machine learning, if you're familiar with that, that's one-hot encoding equivalent. Okay, so again, we start from a number of bits. We select the vector. This vector with only 1, 1 selects the column, and then you send that over time. It's a different rendition. The problem with creating a code book this way and keeping track of the code book is your matrix is huge. If you're sending 100 bits, your matrix is, the width of your matrix is 2 to the 100. And the length of the height of the matrix is the number of symbols you want to transmit on your channel. So it's good as a mental way to think about it, but it can be a little bit challenging. It's not a practical way to do encoding. So Joseph and Barron introduced this sparse regression code, or in 2012, and what they said is, well, I'm not sure that's what they said, but my interpretation of this scheme is that let's think of a matrix of code words that produces code words, but instead of having one hot encoding, I'm going to separate my vector on the right into sections, and I'm going to have one index per section. So here I have L sections, and the number of bits per section is B over L, so the total number of bits remains the same, but this vector has now L non-zero entries, and the code word that you send is slightly more structured than it was before. When you fold this vector over the matrix, it's going to identify L columns, sum them up, and that's going to be the vector that you send. So the reduction into the size of the matrix is quite scattering. So the length, the number of columns that you need to be able to support this scheme is going to be L times 2 raised to the B over L. And so practically, when we started working on this problem, in fact, we were working on a slightly different problem. We used this to limit the complexity of the system. So if you have 2 to the 128, let me ask a question to you first, since some people here work on compressed sensing. So if you want to do a compressed sensing problem using commodity solvers that are available, what's the size of a matrix that you could deal with? Roughly speaking. Okay, let me ask an easier question. If I have a one sparse compressed sensing matrix with a matrix that has 2 to the 128 columns, can I put that into my solver? Well, that's a little bit ambitious. But 2 to the 16, for some structure matrix, you can start to deal with some algorithms. Okay, so then you get, so these numbers are partly informed by what you can do on a typical computer. So you get 2 to the 16. So for a certain problem, 2 to the 16, you can start to use commodity computing. So we divided the vector this way, but if you look at the reduction in the number of columns, it goes from 2 to the 128 to 2 to the 19. So it's quite a reduction. Okay, so that's part of the motivation for this sparse regression code. And again, a lot is known about sparse regression code, and this is not my work, so I have to give credit. It was shown that the sparse regression code introduced by Joseph and Barron were shown first to achieve capacity, but then they were shown also to be amenable to a low complexity through approximate message passing. And there's, I would say, at least 2 cornerstone papers, and the references in this talk or this summer school, they're not extensive, but one of them is by Barbier and Sakala, where they show that approximate message passing is amenable to, sparse regression code are amenable to approximate message passing decoding with good performance. And here they call it superposition code, but these are the 2 names. Sparse regression code and superposition code are the same thing. And this other paper by Raj, Greg, and Ramji, they show that also that when you use a Spark structure, a sparse regression code, with a certain power distribution and apply approximate message passing to it, with a low complexity algorithm, you can get capacity achieving performance. That's quite quite an achievement. And in the later of the two paper, they use a scheme that if you look at their scheme, essentially what they do is they have a denoiser that's based on a blockwise entry denoiser, and then that's based on the conditional expectation. And that conditional expectation is informed by the noise that you can compute through the state evolution that we've seen yesterday. So this is already established. If you look at this, maybe we'll see a few of these diagrams. They look similar, so I'm trying to do a visual way. So if you think of it this way, you're going to have y, and then here you have a times your previous state. So this is your z is, or z is the residual. So it's y minus what the part of the observation that you can explain. So this should be somewhat familiar. And then, but it's also added by the computation of the Onsager term. So the state comes through. You have this div operator that comes from Stein's lemma, and you multiply it by the previous z, and then it adds up. So that's the Onsager term here, highlighted in a dotted pattern. From your residual, we know that you can compute the effective observation by taking A transpose of z and adding the previous state. So R is your effective observation that you can go through a denoiser. So for their denoiser, they control their block size. They do a blockwise denoiser, it's slightly different than what we've seen. We've seen a symbol-wise denoiser, but the theory of M can be extended in various ways. This is one way, and then they use an mMTC version for that, or an approximation thereof. And because they apply it on a block per block, they can do the mMTC quite well. So one way to think about it when you construct the SPAR code is the following. So one way to enhance a SPAR code would be the following. You start with your information bits, and then you encode the bits with an outer code. And then you divide them and do the SPAR. So what we're interested in is knowing if there are many systems in communication that use a juxtaposition of two codes through a concatenated scheme. So we want to look at maybe, can we enhance, draw from the past successes of concatenation and see if we can enhance the empirical performance of sparse regression code. So again, we are going to look at redundancy. First encode, then split, then do Spark. It turns out that one of the natural picks, although it may not be the only one, but one of the natural way to pick your outer code is to use an LDPC code. And one thing that seemed natural to me is to pick the LDPC code over an alphabet, a non-binary alphabet. So here that's denoted by FQ. That matches the size of your blocks. Why? Because then there's a natural mapping between your symbols of your encoded vector and your block. So it seems quite natural. And then to go from here to a likelihood on your symbol is also very natural. It is not the only way to do it, but it is one way to do it. We want to study this object. That's going to be our objective. And this will leverage two codes that now have been independently very successful. So first, LDPC codes are typically decoded through message passing algorithm. And there's a lot of literature on message passing algorithms. And there's these two beautiful too beautiful, the top 2 papers about message passing algorithms, if you've not seen it, that I recommend. But what is going to happen here, what do I mean by message passing? So here you have the symbols that are the symbols of your coded vector. When you created your code word, you selected the symbols in a way that has redundancy. And you added the redundancy in a way that is easily locally checkable through check nodes. So what do you do? So you get kind of these observations that are coming through the channel. So for us, we're working in a higher dimension LDPC code. So these observations, they give you, in some sense, a probability of every symbol for that high non-binary LDPC code. And then you want a principal way to pass information back and forth between your variable node and your check node in a way that steers your decoding in the right direction. On this graph, the local information is denoted by alpha L. And then you have 2 types of messages. You have a message that goes mu from variable node to check node, and a left message that goes from a check node to a variable node. So you can see a few things about this graph. One of them is, typically this layer is not shown, but because I'm not a coding theorist myself, I work with coding theorists, it's easier for me to think about how this process gets started. Many of you are probably familiar with some LDPC codes, binary LDPC codes. It's very similar with what's happening here, except that on a binary LDPC codes, you only have 2 possible symbols, and probability live in the simplex. So you only have 1 degree of freedom in a probability that has 2 symbols. So you only need to send 1. So when you do message passing decoding for binary, you typically see a scalar being passed back and forth. And then there are ways to do that quite well. When you have a non-binary LDPC code, you're actually passing vectors. Okay. The last reference here gives you, it's a reference to a book by Richardson and Urbanke and called Modern Coding Theory. And in that, there is everything you need to know about LDPC codes in some sense. How they get close to capacity, how to do these algorithms, message passing algorithms, specifically for LDPC code. So very good code. So we have on 2 sides codes that are capacity achieving. So what's the possibility? The possibility is then to look at was there finite block length performance, or how good do they get with block size or something like that. Okay, so our goal is to see how this is going to jibe with approximate message passing. Okay, so now we have 2 very strong, or 1 theoretically strong way and 1 both theoretically and practically strong way to encode messages. And we are going to try to get a union of the 2. So what are the benefits of LDPC codes? They're capacity approaching, there's very efficient decoding, and they're used in practice extensively. What are the good sides of sparse regression code? They're capacity approaching, there's efficient decoding. They don't have as good low block size performance, so they're not used that much in practice. But they have good properties. Okay, so I also want to say that our group did not create this marriage. Some other researchers have looked at the concatenation between the 2, and that includes Lee Ping that has done extensive work on that, and I'm citing one paper, but there are several of these papers. Liu, Liang, Ma, and Ping. And in this paper, they show that this structure can be capacity achieving as well, or not exactly the same structure as, but a structure that does concatenation can be capacity achieving as well. But in their proof, it relies on an assumption that this system will fulfill a behavior that's like the one that was derived by Reeves, Galen Reeves, and Henry Pfister about how the replica method applies. So in some sense, there's an assumption that it relies on, but if that assumption is correct, then the code will achieve capacity. Okay, so let's look for us. We're thinking that there may be gain if we're able to embed the structure of the outer code into the denoiser. This is a new set. There was some study of concatenation that did not create a denoiser that is attuned to the outer code. But we will try to get, instead of having first decode, say, the sparse regression code and then decode the LDPC code in succession, we're going to try to use our knowledge of the unsagger term and approximate message passing to have them decode jointly. So again, this is just a recap of how we get the sections. So you take a binary code, and for an LDPC, you get to a certain symbol, and then you do one-hot encoding with respect to this symbol. Now, let's see where we're going. So I want to do a three-step of what we're going to do about how we're going to get to decoding. So this diagram is from yesterday. So I want to make sure that we're grounded in what we've done yesterday. That's our iterative scheme that led to the optimum solution for a very simple problem. And I said yesterday, I'm going to introduce this third step where you have an effective observation so that it looks like what we want for tomorrow. Again, you can see that this diagram comes with y, and then from y, you're going to subtract a times where you believe you are in terms of state. That gives you the residual. From the residual, you multiply it on the left by a transpose, and you add the previous state, you get the effective observation. And then for this toy problem, the residual is equal to the next state. Okay, so now for our problem, we know that the outer code is an LDPC code. So what can we do? The first thing that we can do is say we're going to denoise. So the difference between this side and the previous side is now we have introduced this denoiser. This denoiser is going to try to incorporate the information that we have about the state. So let me draw an analogy with what we did earlier this morning. The information we had about the state this morning was that it was sparse. The information we have about the state now is that it comes from an LDPC code. So we're going to try to create a denoiser that takes into consideration the graphical structure of the LDPC code to enhance the estimate. So let's go around the graph one more time. So you have y. From y, you subtract 8 times where you believe your state is. That gives you the residual. The residual is then transformed into an effective observation. And the effective observation goes into your LDPC decoder. Now, at the onset of this problem, the LDPC decoder is not going to try to decode the entire thing. It's just going to try to do a bit of a few iterations to look at the local property of the vector and see if it's consistent or see if it's not consistent. And then one of the properties of an LDPC decoder is that it returns a soft estimate, so you can draw at any iteration the value that you believe in a soft way what the vector would be. So you're updating the state. So although the state for us as a sparse structure, ultimately, we're not taking a hard line at the sparse structure like we did with the soft thresholding. Rather, we're just leveraging our knowledge of the outer code and its dependencies to steer the estimation in the right direction slightly. We're missing one part. We're missing a part that's the unsagger term. So we're going to try to come up with an unsagger term for this to make it a legitimate AMP. This unsagger term is what we've seen yesterday. This is what we've been building this week, except that now it's in a somewhat unusual problem setting. And the unsagger term for us, how we talked about it, was heavily inspired by this beautiful paper by Bayati and Montanari, which most of what we've seen is based on this paper. But I will say that this paper is not particularly accessible, so I was trying to simplify some of the presentation. Yes? That's true. I forgot to mention. So for the theory of Spark, that matrix, that code book, is for the theory where you seek to apply approximate message passing. You take it to be Gaussian with the exact same assumption that we had yesterday. So at least at the analysis level, you want to match the theory of approximate message passing. In practice, and I'll come to that later, we do something slightly different. I'll talk about it. But for now, let's think about it as our problem is drawn at random from a Gaussian matrix, but it's known both at the transmitter and the receiver. So it's common randomness. It's at random, but at random that's agreed by the transmitter and the receiver.
Now, you have a vector where you divide into blocks, and each block has only one active element.
Yes.
So, how do you decode using AMP? Like, are you taking each subblock and run AMP on each of them, or you give whole vector and AMP recovers?
Yeah, so we'll get to, so now you're ahead of what I was going to say. So you're saying, why would you do that?
Yeah, because you said that both are capacity achieving and both have efficient decoding. Then what's the advantage of combining both of them? And what are you looking for in that?
Right, so
How is it even like possible? I don't understand. Like, how can you mix them?
right. I mean, these are all good questions. So I was pointing out that they're both capacity achieving. That's always a beautiful accomplishment for an information theorist to show that a structure is capacity achieving. So we're not going to beat them in terms of capacity. That's a hard wall. What we're trying to see is if, so Spark, for instance, is known to have slow convergence to capacity as a function of block size. When you say a code is capacity achieving, typically you're really talking about a code family that increases in some parameter, and as it becomes larger, the performance gets closer and closer to capacity. So here we're going to try to look at small block length performance. Then you had a second good question. So the second question was, why would we, what are the possible advantages of this? So the practical matter. So I'm going to present today for a single user mostly. There are at least 3 families of codes that are, well, very successful for, and there are many. Okay, I can name 3 families of codes that have been used extensively for short block length. There's convolutional code, there is LDPC code, which are part of the standard, and polar codes have phenomenal performance for short block length. So why do something like this? Is that likely to, and there's been a lot of engineering in each of these classes to find very good codes. So are we likely to come up with this scheme and blow them out of the water? No. I think this is an interesting notional coding algorithm to try to see what we can get out of it in terms of performance, how it compares, and we'll get there in a minute. But also there seem to be some advantages, some natural advantages. So for instance, if this code provides natural shaping in some sense, so we know that if you have a high capacity channel, then you cannot use binary symbols, for instance. So you have to do some constellation shaping. This provides some natural shaping in terms of this code. And it provides a platform to have multiple concurrent users. And the hope is that it can do things like, or my hope is that it can do things well like asynchrony. Tomorrow we'll see where this structure came from. It actually came from a harder problem. And then after working on the harder problem, I thought it would be natural to make sure that it works well for the single user problem. Then you had some other questions, but I forgot. You asked more than 2 questions, so I forgot that. Oh, okay, so that was a good question as well. So code have different properties and they perform well on different type of noise. And many coding systems have a concatenated structure where one code tries to get good performance and the other code does the cleanup in some sense. We'll see that here to some extent. But I mean, I don't know how much we are collectively familiar with coding, but one example of that would be something like Reed-Solomon codes are wonderful for block erasure. They're MDS codes, so if you have a few blocks that are erased, they perform really well. But if you take the same number of bit error and you spread them uniformly over the different blocks, they will not perform that well because that structure is really amenable to block erasure. Convolutional code work well for noise that's spread well, but when they fail, they tend to fail and there's a path deviation from their trellis, so they will have maybe a succession of error before they get back into the trellis. So it's just that you have codes that have different properties and you match them to try to take advantage of both. And then you said, how do you do it? So typically, they're used in succession, or often they're used in succession. You encode with one first, and then you get the output, and then you encode the output with the other. And that's exactly what we're doing here in our problem. Okay, so this is where we were yesterday. For our M problem, we need something that's slightly more powerful. So the paper that was there on the previous slide and the theory that we talked about yesterday applies the denoising function component-wise. For instance, when we did compressed sensing, it was applying the soft thresholding component-wise. It's a separable function. Our function lives on a graph that takes into consideration many of the symbols. So it's not component-wise. What we need is a more powerful result. And we use specifically a result by Berthier, Montanari, and Nguyen about state evolution for approximate message passing with non-separable function. I don't think that I want to say much about it other than the theory that we saw yesterday has been extended in many ways, and that's one of the way, and then we have to use this more powerful way to justify the application of approximate message passing to our result. The structure of our AMP is going to be very familiar to you by this time. So the first one is the computation of the residual with the unstaggered term. The second one is the effective observation, which asymptotically should go to Gaussian. That we know that it should go to the true state plus some Gaussian noise at every iteration if state evolution and AMP is proper. And then our denoising is going to be based on belief propagation. So ideally, if complexity was not an issue and you had this coding structure, what would you want to do maybe? Or one of the first guesses that people are inclined to do is to say the denoising should ideally be maybe an mMTC denoiser. So that would be great. But the complexity of the mMTC for a code that has a graph structure with redundancy is cost prohibitive, just because it becomes a combinatorial object, just like it was not possible to use the optimize over an L0 norm. It's not possible for us to optimize over the entire codebook. Because what it means, the complexity is, it means you have to do one computation for every possible code word, essentially, and then sum them up. And then that's just impossible. So the proposed denoiser that we use belief propagation. And let's say we do n rounds of message passing. So the estimate that you will get out of your denoiser, I want you to think of, you have this bipartite graph that we had on the previous slide a few slides ago. And on one side, in circle, you had variable nodes, and on the other side, you had check nodes. And what I want you to do is do this mental exercise that you're going to pinch one variable node. And then you're going to lift it up slowly. And so in the top layer in your hand, you're going to have one variable node, and the next layer, you're going to have check nodes that are the square. Below that, you're going to get the variable nodes that these checks are attached to, and so on. And we're just going to go a few layers into this. So this is the computational tree for that specific variable node. This is what's depicted over here. It says, if I want to compute an estimate for the value of this variable node, and I do only a few rounds, what is going to happen is I'm going to take into consideration the information only from the top layers of the computation tree. Then I'm going to say something like this. I'm going to assume that the loops in my LDPC codes are long enough so that when I chop my tree, considering only the first n iteration, there is no loop in the top part of the tree. If that's true, then the estimate that you get here, taking into consideration all the variables that are in the tree, are essentially the mMTC based on the information contained in that computational tree. It's not the same as this one. This one is the mMTC contained in the entire graph. This is the mMTC computed in the computational tree up to a certain depth. But we're hoping it's good enough. It's a low complexity implementation. Why? Because when you do message passing, you compute the estimates for all the variables at the same time through belief propagation. Okay, so that's a natural estimate, but it's a non-separable estimate. What are the actual functions that you have to do? So all I want to say is there are two steps. There's the function that you must compute at the variable nodes when you do message passing, and there's the functions that you must compute when you add the check nodes. So at the factor nodes or at the check nodes, the information that you get, so remember that we're passing vectors of probabilities for us. So it's just a convolution. It's a convolution. It's not the usual convolution. It's a convolution over FQ, but it's a convolution nonetheless. And on the variable nodes. Okay, what would it be good for it to be a convolution? What do we know? What is fantastic about computing convolution? A fantastic way to compute convolution with low complexity. The Fourier transform, we have a low complexity way to get to this. So this is not going to be a Fourier transform, but it's going to be a transform in a similar way. So we have a very efficient way to do that even for very long vectors. That's very beneficial. And for this one, what you have to do to compute the information that you're going to pass to other nodes is a simple Hadamard product, and then you divide by a normalized version of it. So this is how you pass message on this graph. And there's also, if you want to draw an estimate from after a few rounds, and you want to say, well, what's the probability vector for this section? You can do it by looking at this BP estimate. And this is what I wanted to say, that at any point in time, you initiate your graph with the observations that are given to you through the effective observations from AMP. You get a graph, you iterate a few times, you look at it by looking at this equation, you get an estimate of your entire vectors. So everything checks out in some sense into saying, would that give us a low complexity path? And so the next question is there like any value to doing a concatenation and trying to do the MBP algorithm as opposed to doing decode one and then decode the other? And we can see that like it depends on the EB over N naught. So when you're in the low performance regime, BP gives you very little if you have very noisy, you have a high noise floor. The reason for that is because you're mixing very noisy vectors at the check node, so you don't get much to it. But as the quality of your channel increases, there's a separation between doing the decoding of Spark followed by the decoding of LDPC compared to doing the decoding of Spark and LDPC through an M framework through denoising with the Onsager term. So that's a first, that just gives us some grounding of is it worth considering a joint decoding through approximate message passing. It does quite well. Okay, so if you want the theory of Spark to apply, you need the function to be smooth. So we talked about convergence yesterday, and we said that if I ground that into Stein's lemma, the application of Stein's lemma itself needed some regularity, and then for the concentration where there was the approximations on the slide yesterday, we also need some regularity on the function. And in particular, you need the function to be Lipschitz. So one of the I would say, challenge that we had in creating this AMP-BP decoding algorithm is to show that BP decoding is actually continuous. It's actually Lipschitz. So what do I mean by that? What you have to show is that if you change, so you think of your computational tree, just like we did before, we pinch one node, everything goes down, we chop it at some level. If you make a small change to a variable node at the bottom, it has to make a small change to your estimate at the top. So it turns out that showing that is not quite trivial, and you need some sort of approximation and kind of a proof that by induction, but it's a bi-step induction. But that's quite interesting. So it turns out that message passing, BP through message passing, as long as you don't go into loops, is smooth enough. Actually, if you go into loops, it may be smooth enough as well, but then the way we prove that this function was smooth enough will not carry, and the computation of the Onsager term may not be super small. Okay, then we're looking for a very low complexity. Oh, reasonable complexity. So if you think of decoding normally, you would start your BP algorithm, and then you start in once in LDPC based on what you've seen from the channel, and then you just let it run, and then you hope that you're going to get the code. That's the way you typically run BP for an LDPC code. So a naive way, or a mathematical way that's consistent for us to use BP as a denoiser, very unusual denoiser, is to collect the observation from the effective observation from AMP, put that into your decoder, let that run for n step, and take it out. But if you do that, every AMP iteration, you then have to run a number of iterations on the graph. So one way to circumvent this is to do the following. Get an observation from your AMP algorithm. This is an effective observation. This is what you're passing to your decoding. Do one round of approximate message passing, but save the state of the graph. Keep it there. Go back to your AMP loop, get a new effective observation, and then change these components that are coming. These are the nodes that are coming from your channel that are fixed, one connection. Change their value to what you've seen just now, and then do another round. And then go back, keep the graph, and then go back to AMP, update the observation on your graph. So this is a very unusual way to decode an LDPC code. But what happens is, if you think of your computational tree, the observations that are at the top are the freshest. They're the ones that you've just seen. If you go down one layer, so through a check node to a variable node, this has an observation from 1 round ago. You go down, this will have effectively an observation from 2 rounds ago. But if you do that, you circumvent the problem of having to run n rounds of BP for every AMP iteration. And the price you pay is you get slightly noisier information lower in your tree. But as you continue with that, these improves as a whole. So we want to, okay, so I'm going to use this graph, although it's out of order. So we wanted to check if you do well with BP1 compared to the one that's predicted by the theory for BP. So this is the BPN. This is the one where you do n iterations by every round of AMP. And in red is BP1. So you can see that the approximation matches, or the low complexity version matches the one that's on firm theoretical grounds quite well. And then I'm going to also answer a question that was asked to me yesterday, or that I don't know, I answered it yesterday. Do you have any guarantees that AMP algorithms are good algorithms? And my answer was, it's not because the theory applies that you're given a good algorithm. So it turns out that I have also designed a bad algorithm. We'll see that in a second. So I wanted to do the following. So if you want to use the state evolution that we proved yesterday, you need to be able to evaluate the variance on your graph. So you want the variance of the effective observation, and then you want the variance of the noise. And these are the two that are predictably good for the state evolution to predict how the performance of your code will be. Turns out that for belief propagation, it's easier to keep track of the mean square error on one side, but it's not easy to keep track of the mean square error on the other side. So you have to do some kind of MCMC type method to evaluate it, which is possible. But if you were to use the LMMSC instead of the MMSC in one of the steps, then you get a closed form expression for the right bound message. This is not a Gaussian linear problem, so the LMMSC is not your optimal decoder. So what do you get? You get a very nice expression that you can go into closed form, and then you can track the performance through the state evolution So remember, the state evolution says if I can keep track of the variance of my two components that are my two observations that are part of my system in this composite, so the variance that is on R and the variance that's on Z, then I can predict the performance quite well. So this is again, this is the story now. The BP affine is the one where I use the LMMSE. The BP affine SE is the BP affine with the state evolution that's available in closed form. These two curves we've seen. So again, on the x-axis here, I have EB over N naught. That's a measure of the quality of the channel. On the y-axis is the MSE of my state estimate. So that's a proxy for code performance. If the MSE is low or goes to 0, you've decoded successfully. The state evolution is the dashed line. Tracks the BP affine quite well. The prediction is good. Unfortunately, it predicts really well a bad algorithm. This, for the ones that we've seen already, those are the ones where you use the actual BP equation. So you get the mMSE over the tree depth. Your performance becomes immensely better, but it's not easy to keep track through the state evolution. So, okay, next slide is to say, well, was it worth it? Does it perform well compared to some benchmark? And when I say benchmark, I want to be, I want to say that like there's only one real benchmark. There's other scheme on this graph. But when you talk about an LDPC code that's in the standard, is something that's been very highly optimized. Our systems have not been very highly optimized. And just to put that in context. On the x-axis here, we have the quality of the channel. On the y-axis, we have the bit error rate as measured at the output after making a hard decision on the code. These, we have 5,888 information bit that are going to be used through 7,350 channel use. And we're using kind of our code is SRLDPC is our code rate is 0.8. So whenever you have so this channel use and information use will set the rate of the code. But if you have a concatenated scheme, you have to decide how much of that redundancy you're going to put in the matrix and how much you're going to put in your LDPC code. Okay, so a few curves over here. The first one is Spark plus LDPC. It's a curve that was put together by the people who did AMP applied to Spark. So they realized that they needed some cleanup. They themselves put a concatenation with another LDPC code. But that's their scheme. But in that scheme, that's the scheme over here, they don't have a denoiser that takes into consideration the structure of the code. So that's their performance over here. In blue, that's BPSK plus an LDPC code that's taken from the 5G and R standard. So if you look at the performance here, that's the blue curve. And then we also wanted to check with an LDPC code with a 4-palm. So if you know a little bit about channels and information theory, you know that when a channel is not so good, having a binary signal does not cost you much. But as the channel gets a lot better, then there is a gap between the performance of a binary code or a code with, not a binary code. If you're using a modulation that's binary, there'll be a price to pay if you're in a high throughput channel. Why? Well, think about it this way. If there's a lot of noise, trying to differentiate between 2 points is already difficult. But if you're in a very low noise setting, you can differentiate easily between multiple points. So as the noise goes from large to small, your constellation has to grow from small to large. So this is why there's also this 4-palm quant where we wanted to give it a fair shot with the distribution. So this is also a code that's inspired by the 5GNR setting. And then this is our curve here. So it performs reasonably well. So that's the story for the performance. And then 10 minutes. Then any questions on how? Okay, so as a person and a participant in the summer school, what can you retain out of this? First, I guess, and I don't know how successful I was, but you can say maybe Jeff was fairly enthusiastic about and nerded out about an SRLDPC code that has in a crude assessment okay performance compared to something that's used in a standard. Okay. But I think I wanted to convey the fact that all the machinery that we've done is not only for the compressed sensing with the denoising that's based on the self-thresholding. It applies to problems that at the onset may not look like they should be solved by approximate message passing. That's just one example of others, of many others. And then I wanted to give you a flavor of what happens also in a wireless setting. So there are some benefits to AMP. So one of the benefits is what if you have two users? So there are techniques for standard codes to decode two users, but for AMP it kind of like seems that it's going to come naturally in some sense. And we got inspired to look at this by one of these papers on ADMM, so I think that came out yesterday. Some people were asking me about connections between AMP and alternative projections or ADMM. But so here the story is going to be slightly simpler than that. So suppose you have two users, and they're known users. They're going to use different code book. So this is going to be one random matrix in some sense, and this is going to be the other random matrix. And as I say that random matrix, I forgot to answer one of the questions that I said I would come back to. So let me do that now as we have two matrices on this side. One question that was asked is, how do you design the matrix? And I said, for the theory, we use a Gaussian matrix. For the practice and for the results that I've seen, what we really use is a Hadamard. We sample the rows of a Hadamard matrix to be able to compute A transpose super fast. So we use a fast matrix. It turns out that although we've not looked at them, there are some results that approximate message passing will apply to matrices that are not Gaussian. Matrices that are sub-Gaussian will work. So the theory we have works for Gaussian matrices, but in practice the results is really for these Hadamard matrices. And that's in some sense key to speed up the algorithm. And now you can see that also for the BP we used something like a Hadamard matrix for your LDPC code when we said that there's a convolution step. So you can speed up your BP through the application of a Hadamard transform and carry your convolution as a product and then doing the inverse Hadamard. So there's a lot of things that are meant to optimize the performance in terms of complexity. Okay, so here we have two users, and think of it as two random matrices that are either sampled Gaussian or independently sampled Hadamard matrices. But the structure is the same. They're going to encode. So my observation why, because it's a wireless channel, users are synchronous, is going to be the sum of the received message from the first user and the received message from the second user, and then that's embedded in noise. And then there's going to be, what do you want? Well, the goal is, given knowledge of A1, A2, and also observation Y, we would like to recover S1, S2. So typically, like there are many schemes to try to do multi-user detection. Some of them would be something like successive interference cancellation. Some of them would be a graph that includes both codes, and then you have to do some channel estimation at the symbol level and get estimates for the symbols on the two codes. There are many ways. But for us, if we stare at this long enough, we realize that we can just concatenate the two matrices, and this becomes essentially a bigger AMP problem. And what do I mean by that? Well, now you can think of like once this is A1, this is A2, this is a vector from the first user, this is a vector from the second user. But I can think of A as the matrix that is composed of A1 and A2. And I can think of the state vector as being composed of S1, S2. So now we're back in business. We know how to solve this problem. It's just a larger version of this problem. So one of the questions now is your denoiser is going to be slightly different because it comes as a BP on two different codes. That's easy to implement. It's as easy to implement as it was for the first one. The only question was, will this affect the structure of the Onsager term? It turns out that because the Onsager term is through the div function that looks at what happens to your denoiser on the main diagonal, it becomes just the sum of the two individual divs, in the sense that there is no relation from the bottom graph to the top graph. So the modification to the AMP algorithm is conceptually trivial. Okay, so you just compute AS1, you add AS2, that's the part of the observation that's accounted for, and then you compute your effective observation individually, you pass them to the denoisers in two separate parts, you bring them together, you compensate with the Onsager term, and it's done. So there's a decoupling that happens. So you can decode essentially in parallel, except, so one block, say the red block, is exactly what we did for the single user. So it's fully parallel, except for at the end here, you have to combine, you have to stack your vectors, you have to combine them, and in this step will be an aggregation. When you compute your residual, you'll subtract the contribution that's explained from user 1, user 2, and user 3. But an implementation, that's very, it's a natural parallel implementation of that part, and that's quite compelling. So this is trying to emphasize that. The question was, my question for this side was, will anything change from the user side? Well, you have to pick their code word, their code book judiciously so that they know they're going to be in a certain noise level. But as far as they're concerned, there's nothing has changed. They encode this just like they would for the multi-user. Okay, so I'm going to try to explain what this slide is about. So we wanted to know the performance of a multi-user scheme compared to the performance of a single-user scheme. So what do I mean by that? We've now created a multi-user scheme. One way that you could do it is through time division multiple access or frequency division multiple access. If you did it that way, then every users would be isolated, and the number of channel use that they could take would be just the total divided by the number of users, right? Because you're trying to divide them in time or in frequency. So if you have 1,000 channel uses and you have 10 users, you can only give 100 to each of them. When you do AMP together, all of them are using, in some sense, the 1,000 channels. So why is it a good thing to look at this? So we know, for instance, that TDMA is asymptotically optimum, but we know that for short block length, it's not optimum. So you don't want to divide too much. Okay, so this is the comparison that we wanted to do. this line over here that says OMA, that's orthogonal multiple axis. So this could be your TDMA or your frequency division multiple axis. So this is the performance that's for one user with, say, one amount of resources. The line in green, this is for two users with twice the amount of resources. Now, two users are taking collectively twice the amount of resources. So if you think of the normalized amount of resources you're using per user, it matches the one that's over here. The blue one is for 4, so you have 4 users, you have 4 times the number of channel uses, but if you view it in terms of how many channel uses do I have per user is the same. So we did a normalized comparison, and then we have the 8 users. And what we did is we ran AMP, got the performance for a single user, got a performance for 2 users, 4 users, and 8 users to see how it would perform. And what you can see is it performs quite well. So first of all, there's not a decay. It's a performance improvement. So it takes advantage a little bit of that fact that TDMA is not optimal for finite block length. It's only optimal. This curve here is the capacity of the sum channel. So this is only to say that it seems to be quite a good scheme. It's a low complexity decoding scheme in terms of the complexity scales with the number of users, and the performance improves as you go. I'm out of time, I think, almost. Yeah, I just have a few more. The rest is notional. So maybe before I go into the notional things, I want to ask you if you have some questions about the multi-user. Yes? No, they're not. They're not. They have like Gaussian matrices, and they're all adding up together. Like this. No. They're not. So let me answer. So the Hadamard matrix is a simple matrix on this length. The codes are used on this way, and then you add several of them. So it's almost like you can think of it as being a Bernoulli matrix. It's a good proxy for a Bernoulli matrix. You disregard we never sample the one code words that has all ones or all zeros. But the rest, if I do the following, suppose I have a large Hadamard matrix, and then I look at a subsample, I take just a few rows, and I look at a column at random. So I've sampled the rows at random, and I look at one column. It will essentially look like a Bernoulli random realization. So it's like so they're adding up in a non-orthogonal fashion. This is definitely a non-orthogonal multiple axis scheme. Okay. So I wanted to say a few things. It seems that cell-free has taken a bit of it's been popular as a model to try to go away from cellular models and have a lot more small cells drawn around an area. And what happens with this is you don't have cell boundaries, so it's not like you're going to have like a defined set of users to decode from. So can you do M for that? It turns out that you can do Spark LDPC code with a AMP BP denoiser for this setting. And then you're going to have to think about like places where users are seen. Okay, so the big message is there's a way to use AMP BP for this problem. Let me explain the small message. Suppose we have a cartoonish example. We have 3 users. User 0 is seen by access point 0. User 2 is only seen by access point 1. And user 1 is seen by both. So how will you go about resolving the decoding for that? So one thing that you have to do, so the observation that's at this access point contains only 2 users. So it's going to try to explain what it sees from 2 users. It's Z, so that's the part that's unexplained. The residual is going to be split into 2 parts, an R00 and an R01. The same thing is going to happen at the bottom. So that part is just, it's doing its job just as if it was a unique cell and it sees only 2 users. That part has not changed from the multi-cell. But then you get the following conundrum. So for the users that are seen only from one access point, you can pass them to a BP denoiser amp, just like we did for a single cell. For this user. For this user over here, the problem is you're going to get an effective observations from 2 sites, because that user is being picked up by 2 access points. So on the back hole, you can take your effective observations from these 2. The theory of AMP, if it applies, tells us that these are essentially the true vector embedded in Gaussian noise. If you believe that the state evolution comes into play, you have the variance of the 2 noise vectors, which may be different based on the site. So what you can do is you can do maximum ratio combining of your effective observation, and you'll pass that into the BP denoiser. And then you get the state, you pass the state to wherever that particular is used. In particular, this state for user 0 only is going to go to this site. The state to user, the red user, user 2, is only going to go to this site, but then the state for the blue user is going to go to the 2 sites because it's captured by 2 sites. With that, essentially what you're doing is you're operating on the graph of interference at the users at a high level. The performance of this scheme is also quite good for the user-centric. So here we have the performance of a single user as a benchmark. And then we have the performance of, this is a site that's being seen by 2 places, and this is, okay, so I should say the numerical results are for a slightly more involved graph than we had 3 users. They come from this symmetric graph. I created this symmetric graph, or Jameson, the student who worked on this, created this symmetric graph because we wanted to have a high number of cell sites with different type of users, but not too many curves to show. So let's see how many different types there are. There's this user that are the same in 3 places. They're only seen by 1 access point. So there are 1 access point users. There's these 3 users, U3, U4, and U5. They're seen by 2 each. And there's this user that's in the center that locally is seen by 3. So we have 3 types of users. These correspond to the users that are seen, the 3 users that are seen by only 1 access point. These are the 3 users that are seen by 2 access points. This is seen by the central user that was seen by 3 access points. This is a benchmark of a normalized with the same resources of a single user. So what happens really? We see that if we run this cell-free version of AMP, the users that are seen by only 1 station are essentially their performance is equal to those of the single users. But the users that are in between benefit. The user that's in the middle benefits greatly. So there's 2 things to note. So of course, the user that's seen benefits greatly, but this user benefits greatly to the extent that it gets to a place where it's helping the 3 users that are seen by 2. And collectively, the effect of the interference from these users is almost as if you had the right code word and you ran successive interference cancellation. because the performance disappears, their interference disappears from the performance of the single users. So that's quite positive. Another twist on that is what happens if your users are asynchronous. So, but with known asynchrony. So we wanted asynchronous, but with known asynchrony. So if you have a self-free system over a large area, you're not going to be able to do symbol synchronization or rough symbol synchronization for all of them. So you're going to have some asynchrony. So we just wanted some benchmark. But also I say that with, so asynchronous systems are more difficult to design well, but it's known to improve capacity. So this is the story, same graph, or a very similar graph, x-axis quality of the channel, y-axis the bit error rate performance. The dash curves are the one we saw on the previous page, and the solid curves are the improvements for asynchronous systems. So for the single user, of course, it's a single user, so there is no benefit in asynchronous. But for these other users, there's side benefits for asynchrony. So, and at the system, if you know the delay of every user, the system is as simple to run as it was for the self-free. Two notes. There's some interesting paper. This paper is from Ramji Venkataramanan, who is someone who's been very inspirational to some of our work, but he's one of the co-authors of the paper that we saw that showed that AMP on Spark can reach capacity. In this paper with Liu and Xie, he uses an MBP algorithm for a coded mini-user system. That's a way that's slightly different than ours, but I thought that that was quite nice that they get some good results with a denoiser structure that was kind of similar to ours. And then there's also this paper from Giuseppe Cari and his co-authors that I would be hard-pressed to pronounce right now, which has a different version, a stronger version of self-free, which uses approximate message passing in a different context, so for on-source random access, with multiple antennas. So these ideas are currently propagating to different corner of the research world. And if you look at the timestamp, so this was just submitted. This paper will be presented at ISIT next month. And this was initially submitted in 2023, but it was revised just recently in 2024. So we're talking about research that's ongoing. And with that, I think that's all I wanted to cover today. I'll take questions. Yeah, so that's a pretty broad question. So I can list a few places where notions from approximate message pass. So let me repeat the question. You said, where can we use it for applications? So AMP has been used for image denoising, for instance. So that has been a successful application. Compressed sensing in many ways. We talked about earlier this week, there's some application to matrices instead of having vectors. So it's been lifted to more general settings where you have matrices. There's some studied problem for spike problems where you have a strong low rank component embedded in a noisy matrix. And it's been used for other statistical methods. Just recently, I think, on Archive, it was used for distributed computation with stragglers where some of your blocks will be removed. And I think that's what I have on my fingertips right now for the usage of AMPs. But the place where it's been used most extensively is definitely in the compressed sensing community. That's where the first papers were published. That's where the good results were. So there it's been used quite extensively. And then I should also point out that there has been some interesting work on that ties AMP to machine learning. So whenever you have an iterative algorithm, you can unroll it. And then if you don't know which denoiser to use, you could hope to learn it. So there's learn AMP where the denoisers are learned. So it's quite a rich, there's a collection of papers that are fairly recent. I would say the last 8 years have been quite productive beyond the early compressed sensing work. But many are for statistical problems. Other questions? Oh, and trying to find the right application to where it fits, that's a bit of a challenge. So hopefully we've seen enough of it so that you can recognize a problem that maybe it can be used there. Other questions? Okay, so then let me talk about I am done with the slide. I just want to say, I think we have a break, 15 minutes, and then I intend to come back here for just a few minutes so that to see if you are interested. So I believe you should have received the notebook already. And maybe some of you have run it already. But the goal of the notebook is not necessarily to run it. That takes seconds once it's uploaded in a Google Colab. It's for you to get a starting point where you could do something, try different things. Maybe try a different denoiser. Something simple that's separable, but what to do about energy instead of L1. There was some questions. I think someone came here and said, what if I have different sparsity constraints for a vector? So you can try to write code for a vector that it would lead you to a self-thresholding that has different thresholds, essentially something like that. So you can see empirically how it works. Okay, so let's take a break, and then we'll try to launch you into some conversation on the Jupyter Notebook, and then that's the plan for today. Thank you.